All right, this one says, gives a graph of v, and it tells you a particle moves along the x-axis so that its velocity at any time t, when t is between 0 and 6, is given by a differentiable function v, whose graph is shown above. Okay, so this is a velocity function. The velocity at 0, the velocity is 0 at t equals 0, 3, and 5. Okay, and that's what it looks like. And then the graph has horizontal tangents at t equals 1 and t equals 4. Okay, the areas of the regions bounded by the t-axis and the graph on those intervals are 8, 3, and 2, respectively. All right, let's fill that in. This is 8, 3, and then this will be 2, like this, that area. Okay, and then just keep in mind, like, the area of this is 8, but if we took the integral from 0 to 3, this would be negative 8, since it's below, just like this would be negative 2. Okay, and then at the end they say at time t equals 0, the particle is at x equals negative 2. Okay, so that's just like an initial position. The initial position of the particle is at negative 2. All right, the first one says, for how many values of t, where t is between 0 and 6, is the particle at x equals negative 8? Okay, so think about, I'm going to kind of label it this way. So when t is 0, x is negative 2. And then think about, this is the change in position, you know, from 0 to 3. So, and since this is below the x-axis, that means the particle, the position decreased 8. So that means here the particle must be at negative 10. Okay, and then the same idea, now it went up 3 from 3 to 5, so this will be negative 7. And then here it went down 2, so that'd be x equals negative 9. Okay, and then this question wants to know, for how many values of t is the particle at x equals negative 8? Okay, we know if it's at negative 2 here, and it's at negative 10 when t equals 3, at some point, you know, by the intermediate value theorem, at some point it has to equal negative 8. One thing, this is a continuous function. So it had to equal negative 8 at some point in between here. Same idea at 3, when t equals 3, the particle is at negative 10, and when t equals 5, it's at negative 7. So somewhere in between 3 and 5, it must have crossed over negative 8. And then same thing here, between 5 and 6, it must have crossed over negative 8. Okay, so we can say, we'll say points on the position function are, so I'm going to just list these points. So 0, comma, negative 2, 3, comma, negative 10, 5, comma, negative 7, and 6, comma, negative 9. Okay, and then I don't know how much to explain. You know, to explain fully, you talk about kind of each interval. You know, so on the interval from 0 to 3, so we can say something like x equals negative 2 when t equals 0, and x equals negative 10 when t equals equals 3. And then you can say, therefore, by the intermediate value theorem, there must have been a time between t equals 0 and t equals 3 that the function, that the position equal -8. Okay. Yeah, and actually I should include that this function is continuous. Yeah, because in order, if we're going to use the intermediate value theorem, the hypothesis is that the function has to be continuous on the closed interval. And so we'd have to talk about that. You know, if it's differentiable, then it has to be continuous, and that you'd have to say that. Okay, and I just talked about, I gave this explanation for just why there has to be why the position has to be -8 on the interval from 0 to 3, but you do the same thing from 3 to 5 and then from 5 to 6. Kind of the same wording. Maybe you can kind of just give one explanation for all 3 intervals if you can find a way to do that, but this is at least the general idea. And so when they say how many values, it's really 3. So I'll just put that. That's the real answer. Okay, the next one says on the interval from 2 to 3, is the speed of the particle increasing or decreasing? Give your reason. Oh, the speed. Okay. Okay, so think about speed is absolute value of velocity. Okay, so if we were going to draw the speed, you know, when you take absolute value of a function, and you're doing it to the graph, taking the absolute value and then graphing it, any section of the graph that's below the x-axis gets reflected above the x-axis. So like this should look something like this, like that. And then we can see one thing, there's a horizontal tangent at 1. So it kind of, so from 0 to 1 it's increasing, and then from 1 to 3 it's decreasing, should be. Okay, and they say, is the speed increasing or decreasing? So now this green part is the speed, since it is the absolute value of velocity, and we can see that the speed is decreasing. Right, this part is decreasing. Okay, and then justification would be, you might just say the slope of the tangent line is negative on that interval. Something like that. Okay, that's the first one. Okay, same graph. They say during what time intervals, if any, is the acceleration of the particle negative? Okay, so acceleration is a derivative of velocity. So they're wondering where, if they want to know where the acceleration is negative, they really want to know where the derivative of velocity is negative. Okay, so the derivative of velocity is going to be negative wherever the velocity is decreasing. So it's going to be decreasing, and we can say that. So since the derivative of velocity acceleration, velocity is acceleration. The acceleration, whoops. Negative. Wherever the velocity is decreasing. This happens on the intervals. Okay, so velocity is decreasing from 0 to 1 and from 4 to 6. Okay, that's it. All right, last one. For t between 0 and 6, find both the time and the position of the particle that's farthest to the left. Justify your answer. Okay, so we want to know when it's farthest to the left. So if you remember that when I labeled that on the other picture, this was x equals -2. This is x equals -10. This was x equals -7. This is x equals -9, I think. Okay, so we can see the position is going to be smallest at when t equals 3. It's going to be -10. It's going to be farthest to the left then. Negative means to the left in this case. So find both the time and the position. So the particle be to the left. T equals 3, and its position be x equals -10. Okay, and then justification. You'll really talk about how, probably talk about how if sorry, there's a bunch of ways to do it. You could talk about how velocity is the derivative of position, and so this is really a derivative graph for position. And so we can see, like, if we made up a derivative graph, like a number line, right? This would be 0, 3, 5, and 6, like that. And if we did a number line, since this is derivative for position, this would be negative, positive, negative. And we can see there's going to be a possible max or min at 3, and then a possible max or min, or a possible min at 3, and a possible min at 6, right? Because right, this is decreasing, then increasing, then decreasing until it stops at 6. But okay, so we can see like either that's going to be the min or that's going to be the min. And then we calculated both, you know, negative 10 and negative 9. So we know the negative 10 is going to be the absolute min. Okay, so I would say something like that. But you'll have the scoring guidelines also. So actually, I'm not going to focus on the explanations anymore, now that I think about it. Okay, next one says, let f be a function that's defined for all real numbers x and has the following properties. Okay, it gives you the derivative, second derivative, and just the function. Okay, find each x such that the line tangent to the graph of f is horizontal. Okay, so we want to know where the graph has horizontal tangents. So we want to know where f prime is 0. So if you take the integral of f double prime, this will be f prime, you know, technically plus c. So we'll do that. So we'll do integral. So f prime of x equals the integral of f double prime, which is 24x minus 18. We integrate, we get 12x squared minus 18x plus c. Okay, and then, so this is f prime of x, and that means f prime at 1, if we plug it into here, is negative 6 plus c, and they tell us f prime at 1 is negative 6. So that means c has to be 0. And then now we can update what f prime of x is, get just putting 0 in for that c. So really f prime of x is just 12x squared minus 18x. Okay, and then so now we've got the derivative of f like we wanted, and now we just want to know where or when this is 0. Find each x that the line tangent to the graph is horizontal. Okay, so we just set this equal to 0. Factor out a 6x maybe. And then we can see x is either 0 or 3 over 2. Yeah. Okay, and that's it. Okay, next one, let f be a function that's differentiable for all real numbers. The table above gives the values of f and its derivative for selected points x on the closed interval, okay, negative 1.5 to 1.5. Okay, the second derivative of f has the property that it's always positive on this same interval. Okay, second derivative always positive. Okay, that means it's concave up the whole time, or it means that the derivative's increasing the whole time. And we can kind of see that the derivative is increasing the whole time, or at least for these select values. Okay, write an equation of the tangent line of the graph of f at the point where x equals 1. Okay, let's do that first. Okay, so we'll be focusing on this point here. Okay, so then if we want the equation of the tangent line, we need the full point, which we have. Point is 1 comma negative 4. And then the slope of the tangent line is just the derivative, which is 5. And that's it. So we'll do equals mx plus b, and we'll plug in that point. And then we'll see b equals -9, and then we'll plug it back in. Okay, so that's the equation of the tangent line. And then they say use this line to approximate the value of f of 1.2. Okay, then they say, is this approximation greater than or less than the actual value? Okay, so let's plug in 1.2. So y of 1.2. 5 times 1.2 is 6. That's -3. Okay, and then this thing's concave up. So anytime you have a function that's concave up and you have a tangent line, the approximation for the tangent line, you can see, is going to be smaller than the actual value of the function. It's going to be less than that. So this will be less than, this approximation is less than the actual value of the function at 1.2. Is that everything? Yeah. Okay. Okay, next one gives a picture. They say ship A is traveling due west toward Lighthouse Rock at a speed of 15 kilometers per hour. Traveling west at 15 kilometers per hour. So this is going this way. So you can see this distance, this x distance, is decreasing at the rate of 15 kilometers per hour. So we could put up here dx dt is -15. And then ship B is traveling due north. Ship B is traveling north at 10 kilometers per hour. So that means y is increasing at that rate. So dy dt +10. Okay, let x be that distance. Let y be okay. Let theta, for number 7 now, let theta be the angle shown in the figure. Okay, find the rate of change of theta. So that's d theta dt. When x equals 4 and y equals 3. All right, so we want to get some equation that involves theta, and then probably want x and y to be involved also, since we know everything about them. So tangent, we'll do tangent. Okay, so that's opposite over adjacent. Okay, so now we'll take derivative. So derivative tan secant squared, and then chain rule, d theta dt. Okay, here we'll have to do a product rule. Oops. All right, derivative of the top, derivative of y is dy dt times the bottom minus the top times the derivative of the bottom, dx dt, all over the bottom squared. Okay, so let's plug in everything. We need to find d theta dt, so we need to substitute everything that we see besides that. Okay, secant squared is the biggest thing to get, like the maybe trickiest thing. So think about secant squared. For secant squared, we can look at this and see that, so they tell us at this moment x is 4, y is 3, and that means this would be 5 at the certain moment that they're talking about. So do you see that cosine of theta would be, cosine theta would be 4 adjacent over hypotenuse, so 4/5. That means secant will be the reciprocal, 5/4. And so we can come back here and plug 5/4 in for secant. Okay, so do you see that we found secant theta without finding theta, just using that right triangle? And that'll be real common in these types of problems. All right, for everything else, we just start plugging it in. So dy dt is 10 times x, which is 4, minus y, which is 3, times dx dt, which is negative 15, all over x squared, which is 4 squared. Okay, so now let's simplify this. So this is 25 over 16. This will be 40 plus 45 over 16. Okay, we can multiply both sides by 16 so that those cancel. And that means d theta dt is just 85 over 25. And this will be kilometers per hour. No, radians per hour. Okay, you could have simplified it to 17 over 5, but remember, don't have to simplify. Okay, next one, particle moves along the x-axis in such a way that its acceleration at time t is greater than 0 is given by that equation. Okay, at time t equals 0, the velocity of the particle is 1 and the position is 0. Write an equation for the position of the particle. Okay. So since derivative of velocity is acceleration, that means that velocity is the integral of acceleration. Okay, so that would be the integral of that function that they give. I'll pull out the 4. Okay, integral of cosine 2t is 1/2 sine 2t plus c. Okay, and then to find that c, we'll plug in this initial condition. So v at 0 is 1. And so we can see if you plug in 0 for t, this becomes sine of 0, which is 0. So this whole thing becomes 0. And that means c is 1. So really our velocity. Okay, we can simplify this. 4 times 1/2 is 2. 2 sine 2t plus 1. Okay, now that we found velocity, we'll do the same thing to find position. So position is the integral of velocity. It's the integral of that thing that we just found. Okay. Okay, the integral of 2 sine 2t is negative cosine 2t. Integral of 1 is t, plus c. Okay, x of 0 is 0. So if you do x of 0, so cosine 0 is 1, so this will be negative 1. Plus 0 plus c, so just plus c, and then that equals 0, which means c has to equal 1. Okay, so we'll just plug it back in here, and that'll be our position. Okay, and that was everything. Alright, I can't remember how many people. I thought most people kind of ended up seeing how this worked, so I'm gonna try to figure out, just try to make sure everyone gets how these work, because these will be quick points if you're given something like this. Okay, so you see you're given a slope field for a differential equation. Oh, that differential equation above. Sketch possible solution curves through these points. Okay, and that's all they want us to do. So it doesn't even matter what that equation is. The only thing we're looking at is the slope field and then these 2 points. Okay, so from this top point, just look how this thing kind of flows. So hopefully you can just see how this works. So that one particular solution would look like that. And then this next one looks like it's like curving here, this way, and go curve in the other way. Something like that. Okay, it doesn't have to be perfect, but it does have to be something like that. It has to be decreasing following an asymptote, and it has to be increasing to the left. And then same thing, this one has to be following this asymptote and then following this asymptote. I think that's what they'll be looking for. Oops. Okay, this next one, function f satisfies that differential equation, and f of 0 equals 2. Okay, the Taylor series for f about x equals 0 converges to f of x for all x. Okay, so it's really like kind of like a Maclaurin series, or it is a Maclaurin series. Converges to f of x for all x. Okay. Find the 4th degree Taylor polynomial for f about x equals 0. Okay, so remember a 4th degree Taylor polynomial will look like this. I'm going to write out the whole thing. So 4th degree, make this thinner. 4th degree Taylor polynomial called P4. Okay, so this will be really f of 0 plus f prime of 0 times x plus f double prime of 0 times x squared all over 2 factorial plus f triple prime of 0 times x cubed over 3 factorial, and then plus the 4th derivative, x to the 4th over 4 factorial. Okay, so look at we have everything in every one of these terms. We have everything. We have x to the 4th and 4 factorial, x cubed and 3 factorial, x squared 2 factorial. The only thing we don't have is these derivatives at 0. Oh, that should be a derivative at 0. And then the function at 0. So we just really have to find each one of these, you know. So f of 0 is 2, so we at least know that. So let's get what f prime at 0 is. And we're given f prime up here. So let's figure that out. So f prime 0 is f of 0 plus 0 plus 1, which is 3, since f of 0 is 2. Okay, so so this f prime of 0 will end up being 3. And actually, let me write this. F of 0 equals 2. F prime of 0 equals 3. So let's find the second derivative, and then we'll plug in 0 into that. So we just take the derivative of this. So the derivative of f is f prime, and the derivative of x is 1. Okay, so that means that f double prime of 0, f prime of 0, plus 1. We already found f prime of 0 is 3, so this is 4. Okay, we'll do the same thing. Take the derivative of this, get the third derivative. Okay, and that's just the same as the second derivative. So that means the third derivative at 0 is the same as the second derivative at 0, which is 4. And we can see if we do the fourth derivative at 0, that's going to be the same as the third derivative at 0. And that's going to be 4 also. Alright, so now we just take all these values and then plug them in here. Okay, so if we do that, we get P4 is 2 plus 3x plus 4x squared over 2 factorial plus 4x cubed over 3 factorial, fourth over 4 factorial. Okay, and that's it. Okay, last question. Let R be the region enclosed by those graphs, the y-axis, and the vertical line x equals 2 is shown in the figure. Find the area of R. Alright, so the area of R is just the top line minus the bottom line. So now we just really have to figure out which line's which. And you can do it different ways. I'm going to just plug in 0. We can see one of the graphs, the y-intercept is 4, and the other one, the y-intercept is 1. So just plug in 0 into one of them. See if it's either 4 or 1, you know. So I'll plug in 0 into the cosine one, because cosine 0 is 1, and then 1 times 3 is 3, plus 2 is 1. So this must be the cosine graph. So let's label that. This is g of x, and this top one's f of x. Okay, so if we want to find the area of that region, we'll do the integral from 0 to 2 of f of x minus g of x. So that's f of x, and then minus g of x really end up being plus 2 minus 3. Like that. Okay, so we'll do... Okay, and then just keep in mind, so these together are 8, so this is really 8 plus the rest of that. So let's do that. So the integral of 8 is 8x. Okay, the integral of this expression here is really just going to be negative 2/3 x minus 1 to the third. So hopefully everyone sees that. And then the integral of this expression is going to be negative 6 over pi. And that'll be sine. Okay. Let me make sure that's right. 5 to 2, and because I'm and that, yeah. Okay. Okay, so now I plug in 2. This will be 16 minus, plug in 2, you get 2/3. Plug in 2, you get sine of pi, and that's 0. So that's it. So minus, plug in 0. When you plug in 0, the first and last ones are 0. So just this one here, plug in 0. That'll be a positive 2/3, I think. Wait, plug in 0, that's -1. -1 cubed is -1 times -2/3 is 2/3. Oh wait, here, sorry. Wait, when I plugged in 2 into this, wait. Oh yeah, that's right. What am I thinking? Okay, that's fine. Okay, and then this ends up being 16 minus 4/3. That's it. Okay. Okay, so next one. Region R is the base of a solid. For the solid, at each x, the cross-section perpendicular to the x-axis has that area from the volume. Okay, this one's nice because to find the volume of a solid, all you're doing is integrating the area of a cross-section. And if they give you the area of a cross-section, you just integrate whatever they give you. So this will just be integral from 0 to 2 of this function, and that's it. Okay, that integral is just ln. Okay, we don't need absolute values since these will be positive when we plug them in. So this is ln of 5 minus ln 3. And I'll just write it ln of 5/3, but you don't have to. Either one of these could be the right answer, or would be the right answer. Okay, and then the last one, write but do not evaluate an integral expression that gives the volume of the solid generated when that region R is rotated around y = 6. Okay, so now we're going to rotate this around y = 6. Okay, so, and keep in mind when we do this, we can, in our integral, we don't have to use what, I've been calling, I just realized, so I've been calling this top one f of x. It doesn't really matter, but that should be h of x. This should, f of x should really be h of x. I don't know why I thought that was f of x. Okay, so I'm going to keep it as f of x. So okay, so yeah, I'm going to call this f of x just to be consistent. Okay, so now, yeah, so now we can just use f of x and g of x in our integral. We don't have to like put this in there and put this in there, which isn't a big deal, but kind of nice, maybe. Okay, and then, so to first we'll see that since if we're going to rotate this region around this line, we can see there's gaps here. So that means we're going to be using the washer method. So if we use washer method, we'll use this formula, outer radius pi times outer radius minus inner radius squared. Okay, and yeah, have to have that pi on the outside, or pi somewhere in there. Okay, so now the outer radius. Okay, so think about, let's pick here, let's pick this point here on g of x. Okay, so if we rotate this region, this line would represent the outer radius when this gets rotated. So now this is kind of one of those radiuses. And then keep in mind, this distance from here to here, that's g of x, right? This whole distance is 6. So that means this distance here, the radius that we want, which is we'll call big R, is really 6 minus g of x. Okay. And then similarly, the inner radius is 6 minus f of x. So that's going to be our integral. This goes now from 0 to 2. Okay, that'll be 6 minus, what was the first one? 6 minus g of x was the outside one. That'll be squared minus 6 minus f of x squared dx. Okay, and they said write but do not evaluate, so that's what you could write.